Alright, so we've just gone over how to use the reference circle to solve problems in simple harmonic motion. In this video, we're going to have a look at another method for solving the same types of problems. And for some of you, this will be easier, and for some, the phasor method will be easier. In the questions in the exams, they always give you the option to either use this method of equations, which I'm going to go through now, or using the reference circle, and they usually provide you with a reference circle diagram to help you. Okay, so we'll call this number 5. Using the equations of motion. To solve problems in SHM. All right. Okay, and what we're going to go through is first describing SHM using the equations for x as a function of time, v as a function of time, and a as a function of time, and then we'll have a go at solving a couple of problems. Solving problems using these equations. All right, so if we imagine a pendulum swinging, for example, and we imagine it at these times, so we have it first going through its equilibrium position, and then swinging out to its maximum position, and then swinging back through equilibrium, and then swinging out to its maximum position in the other direction. So this is t equals 0, this is t equals t over 4, this is t equals t over 2, and this is t equals 3t over 4, and I'll just draw the last position as well, like this. And this is time equals a full period. So in this case it's going that way, and here it's going this way, and here it's going that way again. Alright, so in this situation what we've got is 0 displacement at the start, and then max displacement, and then coming back through 0, and then max displacement and negative, and then getting back to its original position and velocity. So in this situation we've drawn this graph before, and I'm just going to draw it again. Oh, actually I'll use the red for the axes. Hold on. So we have a set of axes like this, and we can split it into 4 sections, and this is now going to be x as a function of time, and this is the time. Maybe I won't write that because it'll get confusing with the units, so we'll get x in meters, and this is time in seconds. And so we can see here time equals 0, the displacement is 0, like so. And then it goes up to maximum, and then back to 0, and then down to negative, and then back to 0. And this is a full time period here. I'll do the labels in red as well. This is a time period. This is 3t over 4. This is t over 2. And this is t over 4. And this is 0. And this is the amplitude. Amplitude, remember, is the maximum displacement that it ever reaches, and it reaches that at t over 4 when it's swung out to its maximum position. Therefore this position is the maximum, so we can label that on the axis as the maximum. Every other time it's somewhere between 0 and that maximum. Okay, this function that looks like this is called the sine function. This is a graph where x is equal to the sine of something times time. So we can figure out exactly what that is. So this graph is represented by I'll write x is equal to a times sine of something times time. And we know that when time is a full period, so when a full period has passed, then this has gone through a full cycle. So when a full period has passed, whatever's in this bracket has to be a full cycle worth of radians. So it has to be 2 pi radians. So we know that this constant before here is 2 pi over time period. That way when little t here is equal to big T, they'll cancel and we'll just get 2 pi. So we'll have gone through a full cycle when little t is equal to t. So this is our function, except this thing here is what we call the angular frequency. So the function here for x is going to be equal to a times sine of omega t. Now the velocity here of this same thing, we can get an equation for that too. So I'll draw a second graph here for velocity in meters per second against time. The velocity time graph is a similar graph as we've seen before, except velocity at this time equals 0 is really big and positive. So velocity at time equals 0 is big and positive. I'll just put these labels in as well. This is t over 4. This is t over 2. 3t over 4 and t. So when time is 0, we have a really big positive velocity. When we've gone through a quarter cycle, it's stationary, so it's not moving at all. And after half a time period, we now have a very big velocity in the negative direction, and so it's going to be down here, and then there, and then there. And these graphs will be familiar to you if you've studied calculus, and they may be familiar to everybody. So this graph is going to look like this. And we can see that graph, a graph of this shape, it's the same sort of graph, it's just shifted along, but this is the cosine graph, so x is equal to a omega times cosine of omega t. Now the omega here might be a bit mysterious, but the maximum velocity that it ever reaches is a omega, and the lowest velocity is negative a omega. And those of you studying calculus will see, sorry, this isn't x, this is v. We'll see that this is just, in fact I'll just move so I can write a little bit. This is just the time derivative of this thing, if you've studied calculus. So v is equal to dx over dt. If we differentiate this and using the chain rule, we get omega times a times cosine of omega t. If you haven't done calculus before, it doesn't matter. All of these equations will be provided for you in the formula sheet, so you will know. Now, we can see that this thing that's before here, cosine of omega t, varies between positive 1 and negative 1. So the maximum velocity that it's ever going to have is a omega, and that's the value that it takes there, and there, and there. Similarly, we can draw the graph for acceleration against time. And once again, like this. And for this graph, the acceleration against time is just the gradient of a velocity time graph. And we also know that the acceleration is really big and negative here, and really big and positive here, and it's 0 at all the other points. So we'll start here. So the velocity isn't changing here at all. So let's go back to there. We see here that the acceleration is 0 to begin with. Here we see that the velocity is changing very quickly, but in the negative direction. And that corresponds to this position here, where the acceleration is really big and to the left. So we're going to have a big negative acceleration here, and then 0 a big positive acceleration there, and then 0. So we can draw this graph too, and it looks like this. And the maximum values for this one here is a omega squared, and here is negative a omega squared. So the equation for the acceleration is equal to a omega squared. In fact, it's not. It's equal to negative a omega squared times sine of omega t. And so this is the equation for the acceleration. Notice that, as we said before, a is equal to negative omega squared times x. Right? If we look at this omega squared here, and this negative sign, negative omega squared times a sine theta is a, and a sine theta is just x. So we can see that this equation that we have for the acceleration is consistent with our definition of simple harmonic motion as well. Okay, so these are the equations. If you don't understand where the equations come from, it is calculus. So if you're not studying calculus, then that's tricky. So a is just dv over dt. But all of these equations are provided for you. So if you can recognize the situation where they apply, then you'll be able to use those to solve problems. And I'll give you an example here of a type of problem that we can solve using these equations. So we have a situation where a kid is on a swing. So we'll go e.g. A kid is on a swing, and the amplitude is 2.0 meters. The period is 4.0 seconds. And he starts at 0 displacement, so he is at 0 displacement at t equals 0, and he's moving right. So this is a lot like the pendulum that we just used as our example to show these ideas. And then we're asked to find his displacement and velocity at, and then we have a few different times. So one is time equals 1.0 seconds. Okay, and we'll use, even though we kind of know what's happening at 1 second, because that's exactly a quarter period, and we're going to use the equations just to show how that works. So we know that for displacement, x is going to be equal to a sine omega t. So in this case, omega is equal to 2 pi over the period, which is equal to 2 pi over 4, which is pi over 2. So x is going to be equal to, the amplitude was 2 meters, 2.0 times sine of pi over 2 times 1. Okay, and then we can work that out using our calculator. So here we use 2 times, and then we'll work this out, pi, over 2 times 1, close bracket, and then we'll take the sine of that, and equals, so he is at, no, I'm in degrees, hold on, I need to redo that. So we'll go pi over 2 times 1, and then we'll take the sine of that, and then times 2, because 2 was the amplitude. So we end up with 2 here, and that's equal to 2.0 meters. And we kind of knew that already, because we knew that we went through a quarter period, and after a quarter period he's going to be at the amplitude, right? Quarter period is all the way out to the end. Okay, and we also know that the velocity should be 0. We can work that out as well and just confirm it. V is equal to A times omega times cosine of omega t. So in our case, that's amplitude was 2.0 times omega, which was pi over 2, times the cosine of pi over 2 times 1. And this cosine of pi over 2 times 1 is 0, but we can just show that. So we go 2 times pi divided by 2 times, and then we want pi divided by 2 times 1, and we want to take the cosine of that. And that gives us a final answer of 0, because the cosine of pi over 2 is 0. So that gives us 0. So after 1 second, this kid on the swing will be at 2 meters displacement, so they will have swung out to their maximum position, and at that instant they're moving at 0 meters per second. Okay, so that one's fairly straightforward, and we've just confirmed that the equations work for that position. And I'll just show you here. So basically a quarter period is here. So they're at maximum displacement and they have 0 velocity. So the equations are consistent with the graph. So for the second example, we will look at what's going on at 3 seconds. No, we won't. 3 seconds is too obvious. So we'll go, let's go t equals 1.5 seconds. So let's figure out what x is going to be at 1.5 seconds. So this is less obvious. This is the kind of thing that we would have used our reference circle for. So we have x is equal to a sine omega t, which is equal to 2.0 times sine of pi over 2 times 1.5, which is equal to 2 times, and then we have pi over 2 times 1.5, and then we want to take the sine of that, and we can see that they are at 1.41 meters. Okay, and for the speed, we have v equals a omega cosine of omega t, which in this case is 2.0 times pi over 2 times cosine of pi over 2 times 1.5, which gives us 2.0 times pi divided by 2 times pi divided by 2 times 1.5, and then we'll take the cosine of that, and we get that the speed is negative 2.22 meters per second. So let's just have a look and see if that's consistent with our graph. So 1.41 displacement after 1.5 seconds. So 1.5 seconds is about here. So we are no longer at 2. We're a bit down from 2. We're at 1.41. That makes sense. And our velocity is negative, and it's negative 2.22. It makes sense that it should be negative. We don't really know what the maximum value is, but I'm just going to explain how to get that in a moment. Okay, so the last thing that I'm going to do, in fact not quite the last thing, is to just explain. So the max values for x, v, t okay, so to find, in fact, let's go black. So to find x max, well, in fact, actually, we don't even need to find that. Let's just go x max is defined as a. That's the biggest value that the displacement ever takes. V max is a times omega, and I'll show you why briefly. So v is equal to a omega cosine of omega t, and cosine of omega t, so this ranges from +1 to -1. So the biggest value this ever takes is 1, which means the biggest value that v ever takes is a omega. So v equals v max. Oh, well, v max is equal to a omega, because this bit here never gets bigger than 1. A max is a times omega squared for the same reason, because the acceleration is a negative a omega squared sine of omega t. And because sine of omega t never gets bigger than 1, a omega squared is the biggest value that the acceleration will ever take. So to find the max values, all we need to do is just use the little bit at the start of the equation. Okay, and finally, there's one little detail that you need to be aware of. So which equations to use depends on the starting point. So if at t equals 0, the object is passing through equilibrium, we use x equals a sine omega t. These are the equations that we have above. V equals a omega cosine of omega t, and a equals a negative a omega squared sine omega t. Okay, so those are our equations if we're passing through 0 at time equals 0. If at time equals 0, the object is at max displacement, we use a different set of equations. They're used in exactly the same way, but we use a different set of equations. So we use x equals a cosine of omega t, which looks like this. And that's because if it's at time equals 0, if it's at max position, we need to start off here. And the function that starts there is x equals a cos omega t. So the reason we've changed the equations is because we're starting at a different point. V then is going to be equal to negative a omega sine omega t, and a is going to be equal to negative a omega squared cos omega t. So both of these sets of equations are provided in your equation sheet. You need to be aware that If at the starting point they're at max displacement, then we use the set of equations that starts with x equals a cos omega t. So if we're asked for the acceleration, we need to use negative a omega squared cos omega t. If, however, at time equals 0, the object is passing through equilibrium, then we use this set of equations. So it depends on the starting point. Otherwise, the application of the equations is exactly the same. And all we need to do to work with these equations is to know the amplitude and the angular frequency, and we'll know the angular frequency if we know the time period, because angular frequency is equal to 2 pi over t, or 2 pi f. Okay, so that's how we use the equations. I'll go through a couple more examples in the next video.